Hello. Can anyone confirm me that whether I'm audible to or not? Please write in the chat box. And please clarify that whether my screen is visible to or not. So what about, yeah, fine. Okay. So, so without any further delay, I will begin the session. So before going to today's topic, let's recall what we have did in the last class. So in the last class, we have demonstrated to you how to calculate the solvation energy of a molecule. So how to calculate the, and then solubility of that molecule in different solvents. We have demonstrated that. So after that, we demonstrated you how to calculate the Gibbs free energy or energy of a chemical reaction. For that, you need to calculate the energy of your reactant. You need to calculate the energy of your overall molecule, and you know how to calculate the energy. Then after, you need to subtract your energy of reactant in product. Then you will get the total energy of your reaction. So based on that reaction, you can check that whether which part of your reactant is more stable, whether it is product or reactant. Based on that, you can conclude that whether that reaction is chemically practically possible or not. So after that, we have demonstrated how to perform the DFT calculations at a different temperature, then different pressure and pH, a different pH value. So we have demonstrated. Then after that, we have demonstrated how to perform the DFT calculations using multiple basis set or mixed basis set. Then we have demonstrated how to perform the multiple DFT calculations at a time. So far we are doing one calculations at a time. So, but even you can do like number of calculations at a time by using Gaussian. We have demonstrated that also. So in today's class, we are going to discuss about, first we are going to talk about transition state calculations. For example, if you have reactions, then how to, we can calculate the transition state of the chemical reaction by using the DFT method. So once it is done, we are going to talk about the IRC calculations of a reaction, like a different intrinsic reaction coordinates. We are going to demonstrate how to calculate those different intrinsic reaction coordinates of a chemical reaction. So after that, we are going to talk about like how exactly the information we got from by this transition state energy or transition state calculations or from IRC calculations or from Gibbs free energy calculations. By using all those information, we can predict the path of the reactions and can predict the mechanism, how exactly it will take place. So after that, we are going to demonstrate you how to calculate the EPR spectra of any molecule. So how to analyze data, we are going to talk about that. If time permits, we are going to talk about the how to do the calculation for emission spectra and fluorescence spectra, all those things. Okay. So now we'll start the calculation of the transition state. Okay. So before going to the calculations, let me tell like what exactly the transition state. So why should we need to transition state? So what information we'll get by doing the transition state calculation? So you all familiar about the term transition state, right? So transition state is nothing but it is one of the point at which the reactants are transferred into the product, right? So the place where the reactants are converted to the product. So at the transition state, your like bonds are partially broken and like some bonds are partially formed. Just the transition state is the one of the highest energy state in your reaction. That is, it represents the peak of the energy barrier. So you can take any kind of reactions. So the transition state has the highest energy in your entire energy barrier. Highest energy means it is highly unstable. Highly unstable means the half-life of your transition is very less. And by calculating the transition state, we can will get the idea about the activation energy. So I think you are familiar with the term activation energy. So activation energy is nothing but the energy required to reach the transition state from reactants is known as the activation. Let's consider uh, you want to like reactants are at lower energy state and the definitely the transition state has a like more energy compared to the reactant. So to reach from this reactant place to the transition state, we need to apply some amount of energy. Okay, so how much energy we are going to apply to reach the transition state? It is known as the activation energy. Okay, so by identifying the transition state of any chemical reaction, so you can understand the sequence of steps, like what is the different types of sequence of steps which is involving in your chemical reaction. That is, you can predict the reaction mechanism, not 100%, but you have some idea about like how it may takes place. Okay, how exactly the molecule bond is breaking, how it is forming, you will get some idea about that. So you can also get the some information about like how energy changes as the reactant convert to products. So when the reactants will convert to product, so at each step there will be change in some amount of energy. So by predicting this transition state, we can predict like how exactly the energy changing when the reactants are converted to the product. So throughout the energy barrier, so the energy will continuously changes. So it will from lowest energy, it will reach the highest energy, then it come down to the lowest energy. So like how the energy, exactly the energy changing, we can calculate that. And I already told that by calculating transition energy, we can easily know calculate the activation energy, right? So but using that activation energy, you can predict the rate of your reaction. So you can predict your rate of your chemical reaction. Usually higher the activation energy, slower will be the reaction, because if the activation energy high, we need to apply more energy. So then definitely the reaction will take place at slower rate. And vice versa. If you have like lower activation energy, faster will be the reaction rate. Like that, we can predict the rate of the chemical reaction. So after performing this transition state, while we perform the transition state, we'll do the DFT calculations, right? But how to check that after performing the DFT calculation, we will get the output file. But from that output file, how to check that whatever the molecule you have submitted, whether it is the correct transition state or not? Because you just keep in your mind. So Gaussian software itself, it won't calculate the transition state of any reactions, and it will won't give the result. Okay. So in transition state calculation, it is like a trial and error method. What we need to do, by using your theoretical knowledge, you have to predict that this may be the possible transition state of this reaction. Let's consider you are talking about some reaction X, and you have to yourself, by using your some literature survey or your knowledge, you need to predict that these are the possible transition state of your chemical reaction. Let's consider by using your knowledge, you have predicted like there are 3 to 4 possible transition states are there, but you don't know exactly which is the correct transition state. Then with the help of DFT studies, we can find out that which is the true transition state of that chemical reaction. So without knowing that, just by if you are giving the reaction, then the software won't calculate the transition state. So we have to predict, then whatever the structure you have predicted, you need to draw the structure of the transition state and you need to submit the job. So then it will do the calculation by using that output file. We need to predict that whether that is the true transition state or not. So now the question will come, how just by taking that output file, how can do? For that, first we need to go for the optimization calculation. Then we need to do the frequency calculation of your transition state. So at the transition state level, not at the ground state level. Then when we do the frequency calculation, definitely will give the vibrations, right? For example, whatever the molecule you have drawn, you have submitted for the calculation, if it is giving the negative imaginary frequency value, okay. So after calculation, if you are getting the negative imaginary, listen it carefully. If you are getting negative imaginary frequency value, it indicates that that is the transition state. Let's consider for some reaction, you have predicted that 4 transition states, and now you don't know what exactly, which is your reaction, which like what is the true transition state of your reaction. In that case, what you need to do, you need to do the transition state calculation for all the 4 transition state. Among those 4 transition state, which one is giving the negative imaginary frequency, that is the true transition state of your reaction. Let's consider, so you have submitted, you have predicted like 4 to 5 transition state, and for all the transition state, you are performing the DFT calculation. Okay. Among those 5 transition state, transition states are giving the negative imaginary frequency and 2 are not giving. Then among these 5, those who are those transition state, they are not giving any negative imaginary frequency. We can easily eliminate them and we can say that they are not the transition state. But among those 3, now we will get the confusion like which one is the transition state. So among those 3, so which one is showing the more transition value, more negative imaginary frequency? So that is the best or most probable transition state of your chemical reaction. In that case, we need to compare the value of that negative imaginary frequency. So I'm talking about negative imaginary, but try to understand like what exactly this negative imaginary frequency is. Okay, so this negative imaginary frequency refers to the like vibrational mode of a molecule that corresponds to the transition state and the potential energy surface. For stable molecule, you won't get the this one, a negative imaginary frequency. Okay, you only for a stable molecule, you will get only the vibrational frequency, which are real and positive value. So if you even while doing the optimization, if you are getting any negative imaginary frequency, it indicates that your optimization is not done properly. So because you are taking the stable molecule and you are doing the optimization. So during the optimization, if you are getting the, that is one of the best way to decide whether your molecule optimization is done properly or not, whether it is converged properly or not. Okay, so I have to take care of that. Okay, so this imaginary frequency indicates that the direction which molecule can move from transition state to the either reactant or product. By calculating that imaginary frequency value, by doing the study of that, so we can predict. So where, what is the way of your reaction, whether it is moving forward reaction or backward reaction, or whether it is a reversible reaction. So which has a more possible way to form a reaction. We can predict the path of the reaction. Okay, whether it like we can predict. So which one is the most a better way, whether it will move towards the reactant, whether it move towards the product. So like that, we can conclude the result. So after that, how that one. So you, if you want to study the, let's consider you are interested to study the reaction mechanism, then definitely you need to go for the IRC calculation. Okay, so after transition calculation, I'm going to show you how to perform this IRC calculation. So IRC is nothing but intrinsic reaction coordinates. Okay, so IRC means intrinsic reaction coordinate. These are the reaction coordinates, internal reaction coordinates of your reactant or your transition state, whatever you are taking for the calculation. So it is like IRC calculation is one of the method. It is used to predict the a path of a chemical reaction. So by using this, performing this IRC calculation, you can predict the a path of your chemical reaction uh, that follows the reactant to the product via transition state, right? So first it will, your reactant will go to the transition state and it is highly unstable. Then those transition state will convert to the product. If your product is more stable compared to your reactant, then such kind of chemical reactions are practically possible. If it is like less stable compared to the reactant, then again it will come back to the your reactant. It will come back to your reactant only. It won't stay in your product state. Okay, so along with that path, we can also get the information about the which is the most energetical favorable route for reaction. So which one route is the best to perform such kind of reactions? You can get the information about that. So along that, you will get the idea about the some kinetic properties of your reaction, some thermodynamic properties of reactions. So these kind of information you can get by performing the these transition state calculations or IRC calculations. Okay, now this is a basic theory I want to explain to you. I hope you understood. So do you have any questions so far? So if you have any questions, please write in the chat box. If you don't have any questions, now I'm going to demonstrate you how we can perform the IRC calculation. Okay. So let's consider any SN2 reaction. Okay. So let's consider any SN2 reaction. So I will take one small reaction because we can't do in this demonstration small time further by taking bigger transition state. So let me take a small SN2 reaction. Let me open a ChemDraw. There I will draw what reaction we are going to take. Uh, so before going ahead, can anyone confirm me that whether my screen is visible to you or not? So please write in the chat box. Okay, perfect. Now, so let me open the ChemDraw. So now I'm going to consider like a small SN2 reactions. Okay. So here first what I will do in SN2 reaction, I will take the uh, chloromethane. I will go with the chloromethane. So this how we can draw the chloromethane, right? Let me get it outside. consider like this a chlorometh. Let and then see. Now take the otherwise let me draw. Okay, it will in camera. It will take more time. So let me draw it on the board. Okay. So let consider. Let me open. Yeah, we'll take the same reaction. Okay. So let me draw it. Yeah, perfect. So as a reactant, let's consider this SN2 reaction. So as a reactant, we are going to take chloromethane, right? So chloromethane is like Cl, CH3. So this is one of our reactant. So then we are going to react this reactant with the bromide ion, Br minus. So when it react with the bromide ion, so we'll get the product, right? We'll get the product as this one. Like it will give the uh, methyl bromide, CH3. We'll get the CH3 Br. Actually, let me do that. So delete it. So CH3Br plus it will give the Cl minus ion, right? So this is the reactant and this is the product of your SN2 reaction. So to convert this reactant to this product, it will follow the one path through, it will convert to this product through one transition state, right? How it will do in the SN2 reaction, what happens? So now, so this bromo group will attack from the backside, right? So it will attack from the backside and then here you will get the Cl minus. So once it attack, it will break. So these are, let me do that. These are the hydrogens, hydrogens, hydrogens. So this is the transition state which follow these reactions. So here chloromethane, it will react with the bromide ion and it will give this transition state. This is the transition state and we'll get this kind of products, right? So here, so from backside in SN2, it will react from the backside here. And here, Cl group is, when attacked here, it will leave. See here in the transition state, this product bond is partially formed and reactant bond is partially breaking. So now what we need to do, so this is already well established reaction, right? So now we need to check that whether theoretically this transition state is favorable or not. So whatever this is like predicted transition state. So let's consider uh, first time you are like doing this reaction and you came to know that you predicted this may be the probable transition state of your reaction. So by performing the computational studies, you need to find that whatever the your transition state you have predicted, whether it is correct or not. So how to do that? For that, you need to draw the structure of your transition state, then go for the calculations. So now we need to draw the structure. So what are the transition state we have predicted? So we need to draw the structure of your transition state. And now you just observe the geometry of this transition state. So it is a trigonal bipyramidal, right? So it is in the shape of trigonal bipyramidal. So So it is a shape of trigonal bipyramidal. So here, this CH3 group, CH3 group defines the plane of the your geometry, and the Cl group and the Br group are present at the top and bottom of the plane. Okay. So now you need to draw the structure of this transition state by using the Gauss wave. To draw the structure, you can consider any trigonal bipyramidal metal fragment and you can construct this intermediate structure. Now I am going to go to show you how you can draw the structure by using the Gauss wave. So for just demonstration, I took this reaction. At the same thing, you can calculate for you if you're doing some new reaction. For that reaction also you can calculate this transition state calculation. Okay, so let me minimize it now. Those who are doing simultaneously with me, open the Gaussian software. So open the Gaussian. And now you need to draw the transition state. Okay, so that is a trigonal bipyramidal shape. The geometry of your transition state is trigonal bipyramidal. So for that, first you just go to the view menu, then activate the builder menu. So once you activate the builder menu, go click on your elemental fragment button. So from here, you can click on any metal. Then from there, you can choose the trigonal bipyramidal. You just click on the iron. So trigonal bipyramidal. So that I had this one is the trigonal bipyramidal, right? You just click here and just click here. Now see, these are like trigonal bipyramidal. Yeah. So now you can modify the structure now. You just click on this elemental fragment. Now select the carbon. Then click on this C atom. Now during our in our transition state, the center atom is the carbon, right? You need to replace this iron with the carbon. You just click there. So see, and now yeah. So now we have replaced iron with the carbon. So now we need to replace all these things with the hydrogen atom. So just click on elemental fragment button. You just select the hydrogen atom. So click on the atom. So now just observe here. When I click hydrogen here, there is a change in the bond length. See, there is a change in the bond length, like here also. So like that, you replace all atoms with the hydrogen. So now we need to, yeah. So this is the CH3 plane. Let me keep it here like this. Now we need to keep chlorine at the top of the pyramid and bromine at the bottom of the pyramid. So now just go to the elemental fragment button, then select the chlorine. Either you can select Cl atom or you can monovalent chlorine. Anything is fine. You just go to select the chlorine and click on this atom. Okay. So now similar way, select the bromine atom. Either you can select a bromine atom or bromine monovalent. Then you just click here. See now. So this is what our transition state, right? Just let me open it. See, so carbon, three hydrogen. This is the plane of your geometry. So we have chlorine and we have the bromine. So like that, you need to draw the structure of your transition state in Gaussian software. And now you can just make sure that whether the bond length is proper or not. So now it is CCl bond, right? Usually the experimentally reported data like bond length of CCl bond is around, it is 2.1 angstrom. Theoretically, it will come around like 1.8 to 1.9 angstrom. So let me check. It will show how much. Usually, theoretically, it will be like 1.8 to 1.9. But the experimental, we know it because CCl bonds are higher. They are highly reported. CCl bond, it is like 2.1 angstrom. It is like 2.2 angstrom. So if you know the experimental data, then go with the experimental data. If you don't have any idea about the experimental data, then go with the theoretical bond length values. So now I just want to change this one. Let me check first how it is, how much bond length is there. For that, you just click on this bond, this button. Then you need to select two atoms where you want to change this. First one, second one. Now see, the bond length of this CCl bond is around 1.76. Now I want to change it to 2.1 angstrom. Then you just click on the, see, now the bond length is changed. Similarly, I want to check the bond length of this CBr bond. So just select 1, 2. Okay. Then you just click check. It is like 1.91. It will be experimental data will be like around 1.2.2 angstrom. So like that, this is how we have prepared the structure of the uh, transition state. So once you have prepared the structure of your transition state, now you are in the good position to submit your job to calculate the transition state of your reaction. So now how to submit the calculation in the similar way. Once you have done the structure of your transition state, you just I will just close it. So click on the calculate, then go to the Gaussian calculation setup. And then here you need to submit the, because you need to calculate the how the energy is changing. First, you need to perform the optimization, then you need to perform the frequency. But for this molecule, I am going to for the opt and frequency calculation. Otherwise, you can first you can perform the optimization, then take your optimized molecule, then perform the frequency calculation. Like also you can do that, but already you know how to do individually. But we never so far we never did optimization and frequency at a time. So I will go for this one. You just select this one, optimization and frequency. So here this time, so when we optimize a stable structure, we'll do the optimization at the minimum, right? Optimize to minimum level. Ground level will do. But for transition state, you need to select this one, transition state burning. You need to choose this transition state. And below that, there you have, like I'm repeating once again. So whenever you are doing calculating the transition state of any chemical reaction, so you have to go for the job type should be opt plus frequency. Otherwise, you can go individually. First do the optimization. But even if you are going let me show it. Okay, for example, if you are doing first optimization, then also during optimization, don't go for the minimize. Okay, you need to go for the transition state. Otherwise, directly at the same time, you can do perform the optimization and frequency calculation also. Okay, then you need to optimize to the transition state. Below that, we have the option for the force constant. So during the reaction, we need to calculate the force constant. There are various options are there. Like default option is there, calculate at first point. At the beginning only, it will calculate the force constant. So calculate at the all points. If you give the calculate at the all points, at each point, it will calculate the transition state. So either you can give it the calculate at first point or you can give it the calculate at the all points. But if you get the more accurate result, if you give this calculate at all points, but at the same time, it will take more time to give result. It will take less time compared to this one. So it will need only Cartesian at Cartesian point, it will calculate the force constant. It will calculate only at the internal points. So I will go with the this one, calculated all points. That's thing. You no need to do anything here. Just you need to do one thing: optimize to the transition state, then force constant calculated all points. Okay. So once it is done, you just click on the method. So here you can see I'm telling now this transition state calculation is a completely trial and error method. So you can calculate your transition state by using artifact method, or you can calculate using the DFT method. You can follow a semi-empirical method, and you can do the calculation by using the different basis set. Okay, for example, if you're methoding the artifact method, and you can calculate this transition state by using various method also. And better if the molecule is a little bit weaker compared to this other, now it is like transition state. I will go with the hot refuck. Okay, so now I'll perform by using the, so far we have did the calculation using the Gaussian DFT method. Even you can do with the DFT method. Okay, there also will get, but if you, for this one, if you go with the DFT method, it will take more time. Not more means compared to artifact, it will take 1 or 2 minutes more. But you can do that. Okay, first I will show you how to perform the this calculation by using the artifact method. Then we'll take one more reaction. Then I will show you how we can go with the DFT method. So let's select the method is ground state. Here we are going to use the artifact method default spin. Okay, you just go with the default spin. Then here I will go with the basis set. As you increase the standard of your basis set, the time required to complete this calculation also increases. So, but I will go with the 3 to 1G. I will go with basic one. Then here, no need to do anything here, but here charge. So here charge will be -1. Okay, because 6 atoms are there, 61 electrons. One, it contains one unpaired electron. So you have to be charge will be -1 or singlet. Otherwise, if you're not giving the charge 0 here, then you need to spin as a doublet. Okay. There are two ways. Either you can mention charge as when you are using the transition state, mention the charge and you make it mention as a singlet. Otherwise, you can just keep it the charge as a 0. Other one, you can keep it your spin as a doublet. You can follow anyways. Now I will go with charge -1. Then spin is the singlet. When it is done, you just click on the title. So just provide the title. So just I will give as a transition state. I will name it as a transition underscore state, transition state. Okay, I will just copy this name, Control C. And then link, no need to do anything here. Just click on the preview button, and you just even no need to give the keywords here. Okay, for example, if you are while using the hot refuck method, no need to provide any keywords. Let's consider if you are using the DFT method. Okay, in that case, without using the keyword, you can run this job. But if you are getting some error, okay, if you are getting some any error like your job is abnormally dead, or if you're getting some convergence error, then what you need to do, you just go with some keyword. In such case, you just use the word keyword as opt is equal to no eigen. OPT opt is equal to no eigen, NOIGEN. Okay, so you need to use while when you are using the DFT method. If you're getting error, otherwise, then also it is no need to use that. If you're getting error, convergence error many times, that indicates that so whatever the basis set you are taken for calculation, it is not supporting for that calculation. Then you need to change the basic set, because in while performing this transition state calculation, you will end up with a lot of errors. Okay. At one run, you won't get the result. Okay. It is completely trial and error method. It will take too much of time. And you have to calculate the different basis set, all those things. Now I will go, no, don't give any keywords. Just click on the submit button. Then click on the save. Here, let me check. I will give the transition state control V. And I will click on the save button. I will save it on the desktop. Let me, yeah, I will save it here only. Okay. Transition state, click on the save button. Then click on the S button. Let me check whether we'll get the result or not. It will take some time, around 2 to 3 minutes to finish the job. But while doing your transition state studies, for example, if you do the calculation 5 times, so 3 times you will get the error. 2 times it will give the result. See, luckily this time the job is completed. Okay, so like the whatever the basis set we have used, whatever the method we have used, so it is sufficient to calculate the transition state of this reaction. But if your reaction, if it transition state is too big, it contains some metal atoms, okay, ions. If it is like metal complex, then such kinds you need to use the multiple basis set. You need to go for the mixed basis set. And yesterday I have explained like how we can do the calculation of such kind of problems. Now I will just click on the OK. And already you know that. So whenever you submit the job, it will create two files. One is a log file, another one is a CHK file. So now you need to do the analysis by using the log file. You just click on S and it will close here. Now it will give the, I will just close it here. Okay. So now I'm going to show you what result we got after the transition state studies. Okay. Whether we got the negative imaginary frequency or not, let me check. Okay. For that, you just have to open your log file, go to the file, then click on the open. Now navigate to your working directory. I have saved it on the Gaussian output file. So now we need to open the, we have given the transition state, right? Now we have to open transition state dot log file. This one, transition state log file. You just select this one, you just click on the open. So once you click on the open, so this is your transition state. See here, let me check. So show error for mine. Yeah, it indicates that because actually, so you have to mention properly while you are drawing the structure of your transition state. You have to draw it properly. Okay, then you have to maintain, check that whether the bond length angle is whether it is properly or not. So what kind of basis that you're using. Okay, you have just take care of all those things. I told them most of the times you will get the error. So if you want to perform this kind of calculation, this transition state calculation, it will take time. So you need to spend some like 1 to 2 months in your Gaussian, then only you will get to understand. Okay. So it is like trial and error method. In one time, you can't understand this and you can't do the calculation. And now let me show. Okay. So this is our output file. See here, there is no interactions. So for transition state after output file, like here we have, there is a bond light. After calculation, it won't show any kind of bond here in between those uh, where is bond breaking and where is bond forming. So let me show here now. Just just to now I'll show you how to analyze the result. Just right click, then click on the result, then click on the summary. So here it will show the various optimized property. It will give the like it will give the detail about all those things. Now we have added the charge, all those things, and here you will get the energy of the complete your transition state. So this is the energy of your transition state, and here see here it is showing that there is one imaginary frequency. If you do the, for example, if you have taken your stable molecule and if you have did the optimization in that summary, if it is you are getting like 1 or 2, it indicates that your optimization is not done properly. But if it is like transition state, then definitely it will show the imaginary frequency. Here we are getting one imaginary frequency. Below that you have the dipole moment and polarizability, and you already well aware with this data, right? So the only new thing we are getting this one. And there is one more option. If you click on here, so it will show the various your thermochemistry related property, thermodynamics and thermochemistry related property. You can find out like at what temperature we did the reaction, what is the pressure of the calculation. So to like what scale the frequency is scaled, you can calculate that this is the electronic energy of your system, total energy, and you can this is the 0 point energy of your system. This is the thermal energy of your system, like thermal energy to energy is thermal correction to the enthalpy, how much it did free energy. So what was the additional keywords here? For example, if you are going with Hartree-Fock method, So no need to give any keywords. If you're doing this DFT, if you're following with the DFT method, then if you're getting the error, then go with the opt is equal to no eigen. Let me write in the chat box. Okay. Opt is equal to no eigen. Yeah, you just find it in the chat box. So this is the keyword you need to use if you're getting error. If you're getting, usually it won't show the convergence error. Instead of that, it show that your previous link was dead abnormally, something like it will show like error something 2070, such kind of things you will get. But you have to do it again and again. You have, because even if you did small mistake in while drawing your transition state, you won't get the result. You have to take care of all those things. Then now you can calculate your thermal energy, what is the heat capacity of system. You can calculate what is the entropy of your transition state. You can, there are a lot of properties. These are the various thermochemistry properties you can get from here. And this detail about like optimization energy, like what is the already while doing the optimization I explained like, so what exactly this maximum force or RMS of force or displacement or RMS displacement, exactly what does those indicates. You know how to do analysis of that. This is the one thing, but the beauty of this calculation is, now just observe here, just go to right click, then click on the results. Now just click on the vibration. See, now we are getting, it is showing one of the negative imaginary frequency. So if it is showing negative imaginary frequency, it indicates that this is the probable transition state. Whatever the you predicted is, that is the correct transition state. The reaction is following through these transitions. The reactant of your chemical reactions are converting into product through this transition state. Now, if you want to visualize how exactly the bond is breaking and how the bond is forming, you just select your imaginary frequency and you just click on the start animation. See? So our reactant is the chloromethane. So this carbon is bonded to this one. So it is breaking, then it is going towards the Br minus and it is bonding from it like this. So like that, you can visualize how the bond is breaking, how the bond is forming with your, if you can just, you can increase, if you know already like how to play with these buttons. So already you have learned all those things. Okay. So you have to make sure that if it is, let me check. Imaginary frequency is zero in my case. So if it is zero in your case means you not did properly. You have did some way mistake. You did some mistake while drawing the structure of your molecule. Otherwise, while giving the charge, you have did some mistake. Okay, charge or assign while assigning the charge or assigning some spin multiplicity, how did some mistake. That's why. Because we know that whatever the reaction we have to, that is a basic reaction of organic chemistry, basic SN2 reaction. And we already know that experimentally it is proved that whatever the transition state we have taken, that is the experimentally proved transition state of that reaction. So, but theoretically we are checking just to show you how we can predict the transition state of any chemical reaction. So we are taking it because for I can't take some larger or big transition state, I can do the calculation. If big reaction is there, then transition state, how to predict? So, like big reaction is like, for example, let's consider usually when if you're a research scholar, you won't do like one step reaction like this kind of like two-step reaction. Like usually we'll go with the multiple step reaction. Let's consider if your reaction contains some 10-step reaction. So to get product from reactant, you need to follow the 10 steps. But there will be for each step, there will be on transition state, right? Then for each step, you need to calculate. From first step, from reactant 1 to you will get the intermediate 1. There between your reactant and your intermediate 1, there may be one transition state. You need to predict. For each step, you need to write the mechanism. And if you're like, if there are chances of getting more than one transition state, then for all the transition state, you need to do the calculation. And then theoretically, especially it is highly useful for those who are working in the area of like those who are interested to prove the reaction mechanism. Okay, for them it is highly useful. If you want to experimentally, if you are doing new reaction, and if you want to support experimentally, you have find something, and if you want to theoretically validate, if you theoretically validate, then it will like you are validating your result at high level. So you can validate your result. But in that case, if you are like more than one steps, then you have to calculate the write the mechanism possible. mechanism, then you have to find the transition state of each steps, then you need to go for this kind of calculation. In that case, it will take more time. In that case, you can't do this kind of calculations in laptop. For that, you need to either cluster or supercomputer. Even can you can do it in like 64 GB system, but it will take some time. You need to invest around like 10 to 15 days for performing this kind of calculations. Even more, even it will take 1 month, 2 months also, depending on like how big your molecules are. But you can do, even if your molecule contain any kind of number of, you can do that. So if your molecule containing like more than 35 to 40 atoms, then definitely go for the artifact. Then in that case, don't go for the this DFT method. So for a bigger molecule, DFT method is not that much suitable. Then in that case, you go for the artifact method. So I hope you understand. I think you got answer for your question. Like that, you need to find out the imaginary frequency. And even previously also we have optimized ethanol, right? And we optimized phenol. In that case, we didn't get the negative frequency. All because for stable molecule, we won't get the any kind of like negative frequency. It will whatever the frequency will get, those are the true frequency and those are the positive frequency. And based on this negative frequency, we can decide that whether it is your true transition state or not. And higher the negative frequency value indicates that it is a like uh, it will indicates like that how good the transition state is. So like that, so you can do the transition state calculation. I hope you understood, right? Like that for all the reaction you can do the transition state calculation. So do you have any questions so far? And here you can just show the displacement too, like show the displacement. See, see, when you click on this displacement, the arrow mark shows that, so which is the product. So this highly towards this one because our reactant is chloromethane, right? And bromide is reacting. The final product we are getting the this one chlorobromomethane, right? We are getting the bromomethane. So when you click on this displacement vector, so by observing that we can predict that what is the path of the your reaction. So by using that path, we can predict what is the mechanism. Like it is this reaction is highly favorable towards this one. So whatever the energy we are getting for this product is it has a lesser energy compared to this reactant. When it has a lesser energy, definitely it is more stable. Then the molecules like to stay in that energy level. It don't want to change its uh, place. So that is like basic concept, right? If you have like less energy, it more stable, high energy, less stable, you know that all those things. So like that, you can do it for any kind of reactions. Okay. I hope you understood. If you have any questions, please write in the chat box. Otherwise, I will now I'm going to show you how we can perform the this one. IRC calculation. So before going to IRC calculation, if you have any questions, please write in the chat box. I think there are no questions. Okay, I will move on to the next topic. Now I am going to demonstrate you how we can perform the IRC calculation. Already I have explained that what exactly the IRC calculation, why should we need to perform the IRC calculation, and what information we'll get by doing the IRC calculation. So let me show how we can do that IRC calculation now. So let me open up those who are doing simultaneously with me. I just open the Gaussian software. Let me. So what if multiple negative frequency means they all are transition state? You won't get the multiple frequency because, for example, it consider because it is moving towards like a bromide ion and chloride ion, right? So it is vibrating in only one direction. Then definitely we'll get the only one negative imaginary frequency. For one transition step, it will show only one negative. It won't show like multiple things. But if it's showing multiple means, for example, multiple when sometimes it will get when, for example, there are like it contain more than one reactive center. Whatever the your transition state is there, if it is like containing more than one reactive center, because here it has only one reactive center in this case, so that's why it is showing only one imaginary frequency. Okay. For example, if there are more than one reactive centers which are present in your molecule, in that case, what happens? It will show more than one. For example, there are two reactive centers, then it will show two negative imaginary frequency. So it indicates that that reaction may either takes place to either of the reactive center. Now, if you want to confirm like which one is the best one, which one is more favorable, you can use your theoretical knowledge. Along with that, so which reactive center is giving the highest value of negative imaginary frequency? Okay, so then you go with that one. Who asked this? I hope you understood, sir, right? So that is the answer for your question. Then, sir, in general, how many negative values get? It depends on the like how many reactive centers which are present in our transition state. It depends on the in most of the cases, if it is like usually we'll get one, but sometimes if you contain more than one reactive centers, so then you will get it depends on that you will get the negative imaginary values. So in case of conductive polymers, chain length will be not be known. Then hard to do the calculation. In case of conducting polymers, yes, chain length will not be known. Then you have to take because whenever you can do the polymer studies, so you can do any kind of calculation with the polymers. We can't take the complete structure, right? So we'll take one monomeric unit, then we'll do the calculation, then we correlate with the whole polymer. Not only this type of calculation, even for optimization also, you can't draw the whole structure of polymer, right? You don't know how many monomers which contain it is a polymer. If it contain like number of more, then you can't do the draw the entire structure of your polymers, but you will take some one monomeric unit and will do the calculation. You have to take only the monomeric unit of your polymer structure. And for polymer is more than one transition state possible? Yes, possible. Like there are various reactions are there. So that reactions will take place then like, but there are chances are there. Okay, for example, if you write some kind of reactions, you can predict like 2 to 3 transition state. Either that reaction may takes place through this one or this one. But in the most of the cases, no two transition state usually they have the same energy. Okay, some have the more high energy, some have the less energy. So which transition state have the very high energy? So it is that is more favorable. Okay, even though there are like multiple transition states, so it will choose the best one. In SN1, two transition state are yes. In SN1, you will get the two transition state. But I told na, but it will choose the best one. If you calculate, if you go theoretically, theoretically you can predict that which one is giving the highest imaginary frequency value. Based on that, we can say that among those two, one is the best, most favorable. Like that, we have to decide that. So it means that DFT does not predict any new transition state, but only what is given in output. Yes, in the beginning only I told. Software itself won't predict any kind of new transition state. Okay. So it will only give the, if you give the structure of your transition state, it will tell that whatever your prediction is there, whether it is true transition state or not. That's it. It won't predict the transition state. If you want to predict the transition state, then you can go for the retrosynthesis where there are various observers are there. Then you can go for the you just follow your retrosynthesis method. From there, you will get to know what are the other different possible ways. Maybe in the future, I don't know whether they will update this kind of studies, but so far we can't predict the transition state by using the Gaussian software. So any other questions? If you have any other questions, please write in the chat box. Okay, I think there are no questions. Okay, so if there are no questions, I will move on to the next topic. Now I am going to demonstrate you IRC calculation. Okay, so those who are doing simultaneously with me, so now open the Gaussian software. So to submit the IRC calculation, so here we need to, usually we'll use the output file of our transition state calculation. Okay. So by using that output file of transition state calculation, so we can predict the IRC calculation. Without that, if you want to predict the IRC calculation, if you want to perform the IRC calculation, first you need to do the transition state calculations. Then only you need to go for the IRC calculation. Now, already I told that by doing this IRC calculation, it will give the path of reaction at different, like how the energy is changing when the reactants are converting into product through transition state. We can predict it. Okay. So to perform the IRC calculation, what you need to do, you need to open the log file of your transition state calculation. So you know how to open, click on the file, then click on the open, then go to your working directory and transition state log file. This one, open your transition state log file. Select it, open. So this is the output, right? So this is the output of your transition state calculation. So in the so for whatever the calculation we have did, we have opened the log file, then we have directly have right click, then go to the calculation, and we have submitted the job. But remember, so whenever you are giving the IRC calculation, don't follow that method. If you follow like that, you won't get the result. So instead of that, what you need to do, first you need to open the log file of your transition state calculation. Then right click, you just keep the cursor on that window. Then right click, then go to edit. From there, you need to copy the structure. Copy the structure. I'm repeating once again. First, open the log file of your transition state calculation. Then once it is open, keep the cursor of your mouse on that window. Then right click, go to edit, then click on the copy. You need to copy the structure. So once you have copied the structure, you just close this one. Close it. See, once you have copied, so it will be it is present in your Gauss week. Now you just draw it. You just paste it here. See, like that. You need to do that. So first you need to open the your output file of your transition state calculation, that is log file. From there you need to copy the structure of your output file, that is how. Right click, then go to edit, from there copy, and then you need to open your new window. If it is window is already present, then you just directly you just click here, right, just left click on your mouse, it will be pasted here. If this window is not there, then go to the file, then click on the new molecular group, then new window will come. Okay, so like that you need to draw the structure of your molecule. So once you have pasted your structure, what you need to do now, here now go to the calculate, then click on the Gaussian calculation setup. Now you need to submit the IRC calculation. Okay, now you need to submit the IRC calculation. Here select IRC. I think so. We have did energy calculation and we have completed optimization. So far we have completed frequency. Even have shown now how to perform the optimization and frequency. We have completed scan, we have completed stability calculation, and we have completed NMR. We are left with only IRC calculation. So these are the different calculation what we can do by using Gaussian software. Now today we are going to cover this IRC calculation. So this finish the your Gaussian software. Okay, you just select IRC. So once you have selected this IRC, so these many options will appear. So here, like follow IRC. So how you can calculate your reactive intent? Like towards whether you want to forward means it will calculate only the forward direction. Reverse means it will calculate for the backward reaction. Both direction means so from transition. Like for example, if you select this forward only, then from transition state, so the forward way of only transition state will calculate the reaction coordinates, the energy value of in the forward direction from transition state. If you select the reverse only, then it will calculate the energy values, energy change in the backward reaction. If you select both, it will calculate both. So always select both direction. So here also there is one option is there, force constant. Like how you have did in the previous case here also. Calculate once, calculate always. I told now always you go for the calculate always. So once you click on the calculate always, uh, here compute a more. Here you need to choose the number of points. So like how many energy points you need to calculate. So as the number of energy points increases, the time took to perform the calculations also increases. For this demo purpose, let me go with like 30. I will go with the 30. Then here no need to, yeah, that's it. Here no need to change anything here. Here also you can do one more thing. For example, if you want to give this, if you want to select this one, let's consider if you give it once, or you can give it the CHK file, you can activate this button and you can give the number. If you select this number, so after each energy point, it will calculate the force constant. If you give the 5, then after each energy point, it will calculate what is the force constant of your reaction. But I don't want to suggest that one. You just go for the calculate. I will just deselect this one. You just go for the calculate always. So these are the things you need to take care while performing the IRC calculation. Okay, I'm repeating once again. You just job type should be IRC. Follow IRC should be both direction. Then force constant, calculate always. Then you just activate this compute more points and then keep an. It is up to you. You can go with the 5 or you can go with the 10. So if you go with the 10, it will calculate the 5 energy levels in backward direction and 5 energy levels in forward direction. If you go with the 20, 10, 10, it will go with the 30, then 15 backward, 15 forward, like it will calculate. So as a number of n increases, you will get the more information, but at the same time, it will take the more time. So that's why I will just go with the n is equal to 30. So once it is done, you just go to the click on the method. So here I'm going to use the same method. So you can use it this DFT method too. So ground state, I will go with the ground state. Then this one is a artifact. I will go use the artifact default spin. Then basic set, I'm going with the basic, and here also charge is -1. Okay. So if you want to keep the charge 0, then you have to keep it as a doublet. So I will keep it as a -1, then it will be singlet automatically. Okay, so it will show here like when I will give the charge as a singlet -1, then it will be singlet, how many electrons which are present, how many atoms which are present, it will give the information here. So once it's done, you just click on the title here. Let me give IRC underscore calculation. IRC underscore calc. I gave IRC underscore calc. Control C here. Then just click on the view. So this is the your input file. Then here no need to give any keywords. Okay, and then you just click on the submit button. So here also we'll get a lot of errors. Let me see whether it will run the job or whether I will get any kind of errors here. So click on the save button, then just give the your input file name, and then click on the uh, save button, and just click on the save button. The same way, how to submit the job. So now the job is going on. It will take some time depending on the your number of n, how much n you have given. Depending on that, it will take the time. Now we have given the 30, right? It will take around 2 to 3 minutes. If the job completes successfully, it will take 2 to 3 minutes. If you get some error, then within 2 3 minutes it will show if there are any errors. But the while doing this transition state calculation, IRC calculation, you have to be very careful. I told now most of the case you will get error, but let me see whether I will get it or I will get the result. So I hope I will get the result. So because I have took all the precautions before submitting the job. Let me check now. So within that time, if you have any questions, please write in the chat box. I don't know how. See, now I got the error here. So usually you will get some while performing these kind of jobs, you will end up with this kind of error. See, severe error message 2070. The processing of the last link ended abnormally. Okay. So if you get like, I will let me try it once again. So if I then also if it is showing like this only, then already have did this job because before this workshop I run this job, I got the result because for the safer side I know that in this case I will get a lot of errors. So because I need to explain how we exactly will get the result, that's why I already have did the calculation. But let me try it once again. I want to do it in front of you. Let me close this one. Close the software. Uh, so my working directory is Gaussian output. Let me open this one. Yeah, this one. So what are the job is submitted with the name? This one, right? IRC calc. I will delete these files because we didn't got the result for these things. I will just delete this one. We have to delete three files. One is the log file, CHK file, and this one. So let me try it once again. Whether it will work or not, let me try it. So I will open the Gaussian software. The same thing. Open the output file of your transition state calculation. There is a transition underscore yeah, this one state log. Open this one. So this is your output. Like then right click, then go to this one. What edit, then copy. Then just close it. It is copied. Then paste it here. Yeah. So this is your output structure. Let me show it here. So this is the structure. So now to calculate this one, you just click on the calculate button, then click on the Gaussian calculation setup, then go to IRC calculation, then both direction calculate once. Let me give, I will go with the less numbers. Let me give, I will go with the 20 because for that it is taking too much of time. Let me go try with 20. Then method go on straight artery fog default spin 321G. This was -1 remaining singlet. Go to title. I will just again I will give the uh, IRC underscore calculations. Okay, then let see. Then just go to the preview button. No need to do anything here. Just click on the submit button. Then click on yes. Then provide the name of for your input file. Then click on the save button. Then yes. Let me check. And if you are getting the error again and again, just the only thing is we don't have other option. In that case, you just try it once by using your Gaussian software. Otherwise, you just reinstall your software. So if you have any questions, please write in the chat box. Yeah, see, again, we are getting the error. Okay, so let me explain. Already have did the job. So how the result you will get, right? So in that case, you have to repeat it again and again, and then you have to increase the, if you're getting the error, then you need to change this like basis set, all those things. What I will do, I will just close it. Okay, but I will show the result. Already have afternoon, I did the um, what is it? We can also do it by creating an input file separately, like we did in variable temperature case. Yes, you can do that. Like that also you can do. So, but it will take time, right? For that, you have to be create your input file that will, but you can do that. You can generate the input file, then you can submit. In that case, the chances of error will be less. You can go that. You can create the input file and you can run the job. You can follow that method also. But for this demonstration, I already have did the job. Let me open this file. Gaussian output here. I will delete this one. Now this is the files we did. Okay, so these are the file. Last time afternoon, I think at what time? So I did at around 6:58. I did the IRC calculations. Sorry, around 5 o'clock. I did the IRC calculation. I got the result. So it will like whatever the parameters I have given now. I gave the same parameter. Okay. Uh, but I got the result. But even there is a small change in your structure, then it won't get. So otherwise, in that case, you just try it by creating your input file. Otherwise, you can just reinstall your software once. So I will show the parameters, like whatever the parameters we have taken now, I took the same parameters. Uh, so for that, these kind of like transition studies and to predict the IRC calculation, Gaussian is not that much good software. For that, you can go for like Gaussian. That's the best one. Gaussian and Material Studio, those are the best software. But let me show these results. Close it. So open the Gaussian software. So once your job is completed, you need to open the log file of your IRC calculation. Let me open it. Like go to file, then you can open. Then here we need to now we are in the working directory. We need to open irc.log. So this is my log file. Then click on open. Okay, so this is the output file. So first let me show result summary. See, here I have used the IRC, I did the IRC calculation. So log file, the same here, like it won't show, but I have used the same thing. I used the -1 charge, the singlet. So same file I have used, but it will sometimes it will give, sometimes it won't give here. See, within like 55 seconds, I'm getting the result here. So let me show. So once you have done the job, open your output file and then right click, then here like you can by here, so see here you can visualize various here. Otherwise let me show here, like you just click here. See, so these are the different structure of your molecule. at a different state, how it is moving. Like you can, these are the various frames. You can like how it is varying. At each point, the structure of your transition state is changing. See here, the as the frame moves here, like this molecule, like carbon atom is moving towards this bromide ion. So like that, you can let me calculate. For example, let just observe. Just by looking that image, you won't find, right? You just calculate the energy of this state, this at energy of this transition state at this state, and energy of this transition state. This let me just right click, then go to the results, then click on the summary. It will give the energy for this one, right? Here, how much we getting? 3056, right? 0.82. Let me check for this one. Go to results, then click on the summary. Yeah. So there for 305682 we are getting. For this one, we are getting the 305681. So there is a slight change in the energy value. So the best way to visualize this one is you just let me close this one. Right click, then go to results, then click on the IRCR path. When you do the IRC calculation, so it will activate this button, IRCR path. You just click here, then you will get this curve. So this is the transition state. The highest energy state of your energy barrier is the transition state. Now this is the actual transition state. So now this curve, this one indicates that this is the direction towards the your Br minus ion. So this is the energy of your reaction energy at different reaction coordinates towards this Cl minus ion. Just observe here. So your reactant is here. Okay. Now just you can let me see here. Let me keep it like this one. See here, it is going towards like this. Let consider it is a transition state. Now let keep it here. So now it is at the reactant. Now it is your reactant. Now just click here. So as the energy coordinate moves, your this carbon is moving towards the this one. You can just visualize here by clicking on each points, because we have given 20 points. That's why it has created 20 points. If you want to calculate the energy of your reaction path at different points, you can calculate at whatever the number of points you want. So based on that, you can check that. So what is the transition state? From that, you can calculate what is the activation energy. So if the transition state is this one, okay, this is the transition state. What is the energy? You just let me maximize it. So 3056.80 hat is the activation energy of this reaction. Okay, so the energy required to reach your reactant molecule is the transition state. Then see again, when I will move this side, see, just observe here. So when I change this one, how it is moving. See, it is moving towards the Br minus ion. Now it is looking good after getting the result. But the thing is, getting the output is very difficult here. You have to do a lot of things. If you do it like 5 to 10 times, you will get the result for one time. Like you have to take care of even for minor mistakes. Otherwise, you will end up with the error. So see, for the same parameters, I got the evening, but now when I submit the job, I didn't got the job. Even for that, this one, a transition state calculation, afternoon I did like 7 to 8 times. So I got the result 2 times. So 5 times to 6 times I didn't get the result. But I submitted now because I want to show you how we can submit the job. So, but luckily now the job is completed successfully. So we have to take care of all those things. Like you can just predict by using this reaction coordinate diagram. So we can predict that what is the transition state, what is the activation energy of your reaction, then what is the energy of your reactant. This is the energy of reactant, right? And this is the energy of product. Let's compare. So your reactant has more energy, right? You just observe your energy profile diagram. This is the reactant. So reactant has more energy compared to the your product. It means that your product is less energy, means it is highly stable. It is more stable compared to your reactant. Okay, highly stable word is wrong. It is more stable relatively. If you compare to your reactant, your product state is more stable because your product state has the less energy compared to your reactant. Just observe this diagram. Even by using this calculation, you can draw the energy profile diagram, and you can say that whether your reaction is exothermic, based on you know that how whether you can either exothermic or endothermic, what kind of reaction is going on. So whether it is a forward reaction, backward reaction. Now just see. When it is transition state, definitely here, like it is in the transition state. What is the energy here? Like 3 point, definitely it will come follow this direction only, because here the energy of your product is less. Definitely it will come like this only. And it will form the bond with this one, and it will form the product, and it will break the bond with this Cl minus ion, and it will give Cl minus ion, and you will get the bromomethane. So like how you can predict the uh, energy required to perform that reaction. I can calculate the transition of state of a chemical reaction. I can calculate the also activation energy of reaction. And by using this one, you can predict the path, how exact path the reaction is taking place, and you can predict the mechanism of your reaction. This is how you can do the IRC calculation. I hope you understood, right? So, and if you want to save this file, you just the way you how you saved, you just right click on. If you want to save it in the picture format, you can save it in the picture format. You can otherwise you can save the data, and you can draw the structure of this. You can plot this graph using origin software. And if you want to show other properties here, you can that how you can scale your, like if you want to change the different units. Here there are no units like here. If you, now it is showing in the hertz, you can represent in kilo calorie per mole. Usually when we talk about the energy, usually we'll go with the electron volt or kilocalorie per mole. So now the energy values are showing in kilocalorie per mole. Then you can compare it in electron volt also. See, and the best one is the kilocalorie per mole is the best one. Now you will get the proper energy, or you can keep it now you can easily compare. And these are the this is a forward reaction and backward reaction here. Then if you want current, okay, then height plot, fixed range, title. If you want to change the title here, you can change that. And if you want to check the appearance, like if you want to let me make here, if you want to change the color, can let me make it. Click here. Then if you want to make points, then if you want to curve, let me make it as okay, then let me line with, let me keep it as like 3. So like that, you can do a lot of things with your, you can play with your spectra, then you can save it. So below that, your RMS, this one is the RMS gradient normalization along the IRC codation. This is a normalization. This is like at 0 point, like what is this one? Root mean square gradient normalization force. Then how it is like here to from here it is going. So here if you compare this one, so here the RMS force will be more. So this one is a, this way is a more preferable compared to this reactant. So, but more than this one, we are more interested about this energy profile diagram. So using this energy profile diagram, you can just you will get some idea about your the chemical reactions you are going to study. So like that, we have here for the demonstration, we took simple reaction. You can do it for that one. In the similar way, if you want to practice, you can follow the same reaction, you can do that. Otherwise you can take one more SN2 reaction. You can take methanol, and you can react with some Cl minus ion, chloride ion. So when methanol is react with chloride ion, so it will give the hydroxy OH minus ion as a byproduct, and it will give the chloromethane, right? So in that case we'll get the chloromethane as a product. So methanol will react with the Cl minus ion, it will give the chloromethane as a product, and OH minus ion as a byproduct. And here you will get the same here what you need to do, same it will then in that case also it will take the trigonal bipyramidal geometry transition state. So in that case what happens, the Cl group will attack from the back side. It will attack from back side of your carbon. Then here it will form the bond. Here it will be Cl group, it will form the bond. Let me consider it is the back side. So here the Cl group will come here from this side, and it will form the bond with this make the interaction with your carbon. So then here, whatever the OH group in methanol CH3OH, right? So let's consider it the oxygen here, like OH group is there, then automatically this breaking of this OH group will takes place. So like that in the same way. And if you want to use, you can take this reaction also. You can do the for practice. You can do that. Otherwise, you can do the this transition calculation by using artifact method. Now we did. You can practice it by using your DFT method. And if you are getting the error, then I told this is a error and trial method. You need to change your basis set, methodology. Based on that, you will get that. Okay. I hope you understood, right? So do you have any questions in this one? Let me check. How to do PS scan? So PS scan is already we have completed, right? So in the last classes only we have completed the PS scan. There like for like 20 to 30 minutes I have explained. how to perform the PES scan. You just go through the recordings of the sessions. Okay. I think uh, I think when we have completed that, I think Saturday. I think Saturday class we just go through that. We have done that one. What is the file format we save as in Notepad? So file format in Notepad means you are talking about the log file, right, sir? So whether you are asking about like log file how to analyze, because for we did like so we did the analysis of log file for the NBO calculation. You are asking this that kind of things or what? What is the file format we save as in Notepad? Okay, you are asking the how to prepare the input file for these calculations. Same thing, no need to change anything. Whatever the calculation is giving, like how you are preparing the input file for the optimization and frequency, the same thing you need to give. Okay, same thing you just for transition calculation, because for while finding the transition calculation, so we are doing the same thing. But here the thing is we are not taking ground state. You have to mention the transition state. That's it. Only that's thing. So how we are mentioning for the temperature and pressure, you have to mention the uh, then you have to mention that transition state. We are doing the calculation with the transition state. So any other questions? So if you have any question, I mean file type like TXT, MXT. Like you are asking in which format we need to save the input file to submit the job through Gaussian, right? That is GIF. That is a GIF, Gaussian input file. So in the say for all the calculation, we are saving it in the GIF file only. Just let me show it. Not only this calculation, whatever the input file you are going to use, you have to save it in the GIF file, that is Gaussian input file. Let me consider we did the ethanol. Let's consider optimization of ethanol, right? Ethanol optimization. Let me check the input file. Show more options, properties. So this is the input file, Gaussian input file dot GJF. Okay, the format is the dot GJF. And if you are, for example, if you are facing to save your file in the .gjf by using Notepad, then even that also explained like how to save your file in .gjf in the previous class. So while submitting the batch collection, in that case, what you need to do, you just first create a draft input file by using the Gaussian software. Then whatever the draft input file you have created, you can open it in the notepad and you can modify that file. Then once you have saved that file, automatically you can save that file in the .gjf form. Yeah. So any other questions? I hope you understood these transitions to calculations, IRC calculation, and reaction method prediction. I don't know how many participants are here. Okay, so let me check still what we are pending with. Let me open this one. Workshop. Let me do. Yeah, we completed these things, right? So all the four completed. So we are pending with these things. Adsorption using DFT method and homogeneous hydrogen. It is I won't suggest to perform this kind of calculation using the Gaussian software. I will explain these things either with Schrodinger or quantum espresso. And we today we have completed this intrinsic reaction coordinates or determination of reaction path and mechanism using DFT method and calculation of transition state. Today we did this one, and we did a salvation energy and Gibbs free energy yesterday we did. This one day before yesterday we did this one, and we have completed these things on the second day of our lecture. So we are left with only these things, and everything is completed. Go there above. Yeah, these things completed. Here these things completed. Here ROA, VCD, ECD completed. Yeah, we are left with the EPR, right? Electron paramagnetic resonance spectrum. Now I will explain how to do this EPR calculation. I will explain. Let me check what are remaining things. Uh, Proton NMR, carbon NMR done. This one is done, done, done. This is completed. UV done. So these are okay. Emission, fluorescence. Okay, photoelectric. Let's first explain this one. If I get the time, then we'll go for these things. Okay. So let's minimize this. Let me close this. Okay. So open your EPR calculation. Okay. So before going to show you how to perform the calculation, so let me understand like what exactly the EPR is. Like why should we need to perform EPR calculation? Give me a minute. So please wait for 2 minutes. I will be back in 2 minutes. Hello. Can anyone confirm that whether I am audible to you or not? So please write in the chat box. Yeah. Okay. So now we are going to talk about the EPR spectra, right? So EPR is nothing but electron paramagnetic resonance spectra. So you can call EPR this paramagnetic spectra, resonance spectra. You can also call it as a ESR spectra. So ESR is nothing but your electron spin resonance spectra. Either you can call it as EPR or you can call it as a ECR spectra. So usually this technique is used to study the materials which contain when it can materials contain unpaired electrons. Okay. That is example like can usually we use this method for like to study the free radicals or transition metal complexes. For example, for organic molecules, we won't use this kind of things. Okay. If it is radical, then we will go for that. So you have to keep in your mind that you need to perform the EPR calculation, that is electron paramagnetic resonance calculation or ESR calculation only if your molecule contain the unpaired electron. It should contain at least one unpaired electron. So then only we can go for the this EPR calculation. So far for the demonstration, we took the this one, right? Ethanol. So for ethanol, we can't go to predict the EPR. Even if you do the EPR, you won't get any results. You will end up with the errors because to calculate that EPR studies, if you want to EPR studies, your molecular system should contain at least one unpaired electron. But if you want to calculate the EPS spectra for your ethanol, first what you need to do, first you need to do the homolytic cleavage. Take ethanol like how we did for like while the calculation of dissociation energy. Like for phenol, we have converted it into phenyl radical, then hydrogen radical, right? Phenol also won't show any kind of EPR paramagnetic resonance spectra. But if you convert, if you perform the homolytic cleavage of phenol or ethanol, it will give the respective radical. Okay. For those radicals, you can calculate the this EPR paramagnetic spectra. Sorry, electron paramagnetic resonance spectra. So what exactly happens like during this EPR spectroscopy? Usually, what happens? So whatever the samples you're taking for the analysis, it is exposed to the a strong magnetic field. Okay. So in the EPR spectra, what happens? So they will take your molecule sample and they will expose it with the strong magnetic field, and they irradiate your that sample with the microwaves. So when they irradiate it with the microwaves, what happens? Whatever those unpaired electrons which are present that sample, they will absorb the energy. Okay, they will absorb that energy, and they will undergo transition between the spin state, because it is completely depends on the transition of a spin state. If there are no unpaired electrons, spin will be zero. If the spin will be zero, then this phenomena won't take place. That's why if you want to study this electron paramagnetic resonance spectra, your molecule should be contain at least one unpaired electron. Okay. So even while you are doing these EPR studies, sometimes your sample will attain the resonance state. Now the question will come, when we can attain such kind of like a resonance state. So usually the energy applied, whatever the microwave energy applied to irradiate with the microwave, it matches to the energy difference between the electron spin state. At that position, your sample will attain the resonance condition. It will come to the resonance state when whatever the energy you are applying, like whatever the energy you are applying through microwave radiation is equal to the energy difference between the electron spin state, then your molecule will attain the this resonance state. So I already have told we can't calculate the EPR spectra for the ethanol. Let for a demonstration, you can take any kind of radical. Either you can go with the ethanol radical, or you can go with the this one phenol radical, or can take any kind of radical. Otherwise, you can go with some of like metal complex. You can take some titanium trifluoride or nickel trifluoride. You can take any kind of fluorides, all those things. Here, I'll just show you how we can perform the calculation, because to perform EPR calculation, you can't submit the job directly through the Gauss view. Okay, so far, like see, whatever the options are there in the Gauss view, the Gaussian software. So I have explained everything, like how to submit the different kind of calculation. Then no option is left here. Okay, so here to calculate the EPR spectra, you need to create the input file. Okay, now I just go to show you how you need to create the input file to perform the EPR calculation, then how to analyze the data. Even the thing is, even after performing the EPR spectra, usually experimentally we'll get the EPR spectra, right? It will show the line like this. That line indicates the spin, how the spin transition is taking place in your molecule. Experimentally, we can get the spectra. But when you calculate the EPR spectra by using the Gaussian software, it won't generate the spectra. And if you want to generate the spectra, in that case, you need to use multi-win. So there is one software called like a multi-win. You can use that software and you can do the analysis. But we are not going to cover that. But I will show you how you can do the EPR calculation. But I'm going to show you now how you need to prepare the input file. Already have done the job, because it will take bit time, because we are using the transition metal complex here. And for running that EPR calculation, what we need to do, first you need to draw the structure of your molecule. Then you need to optimize your molecule. Then you need to take the log file of your optimized structure. Then you need to do the frequency calculation. The second step. Otherwise, at a time, we can do both uh, optimization and frequency. Then whatever the data you're getting, output data, you need to use that log file. By using those coordinates of your optimized structure, you need to create one more input file to run the EPR calculation. There you need to mention that you have to calculate that EPR calculation, and then it will do the perform. So it will take around like if I take for this one titanium trifluoride. So it will take around in my system it will take around like 15 to 20 to 25 minutes. So I can't wait for so long in this live session. So that's why I already have did the job. Now I'm going to show you how you can do the analysis of that result, how you can create the input file. Input file is creating same thing. Okay, you know how to optimize, right? You know how to do the calculation. You just draw the structure of your titanium trifluoride. Let me open it. Already I did, I think somewhere I did. Yeah, this one is a EPR study. Let me open this one. So these are the my optimized structure. You just click here. So first I prepared the input file for conduct the optimization. Let me open it in the notepad. Uh, Edit with notepad plus plus. So here. So by this is the input file to run the uh, optimization plus sequence frequency calculation at a time. So yesterday while preparing the input file, so I have mentioned the here like this basis set was present at the bottom of these coordinates. So that is the one method. Directly you can prepare like this also. Either you can prepare your input file in this manner, or you can follow the previous one also. You can in both the way you can prepare your input file. So here I am giving both method and basis I am giving here only, and then I am giving like optimization frequency. And this calculation you no need to prepare even input file too, because you need to perform the optimization and frequency calculation, right? We are taking here like titanium trifluoride. You can just draw it here only. Let me show how to draw the structure of that. Titanium trifluoride. You just go to your build menu, like view menu, then activate the build menu here. Then go to your element of fragment. Here, choose the titanium. Let me check where it is. Platinum, iridium, gallium. Yeah, here, then we are going to the trifluoride, right? So then just you take trifluoride, this one, then click here, you just click here. So this is the uh, titanium. Now we need to replace all this with the fluoride ions. So now this is the titanium here. Then just click the element of fragment. So here, go to fluorine, then select atom or monovalent fluorine. Like so, this is the structure of titanium trifluoride. So now we can go and submit the job. Same thing. First, you need to do the optimization, and now it is like neutral, and the spin is the doublet. The same thing to calculate the APR spectra. Uh, how did the optimization for your ethanols? The same way you need to optimize first, then go for the frequency calculation. Otherwise, simultaneously just go to click on the calculation button, calculate. Gaussian calculation. Here you just directly go to the opt and frequency. So here you can go for the minimum only, don't go for the transition minimum. Here no need to do anything here. Then go to the method here, ground state Hartree-Fock. Otherwise you can go with the ground state, you can go with the DFT method, you can follow anything. B3LYP, and this one is the 6311G, like that. It is up to you. The same thing you need to do the optimization and frequency calculation. So once you have performed the optimization and frequency calculation, it will generate two files, right? And now I won't run the job, just I'm telling like how to submit the job. So after that, you will get the two files. One is the log files and the CSK file. And you know that we need to do the analysis by using the log file. Now open the log file in your Gauss wave. So once you open the log file, let me open it. Already I did the calculation. Let me close it. So now I'm going to open the log file. For that, what I will do, let me go to the file, open. So it is in the EPR, right? I need to go on the desktop. Yeah, desktop question, this one, EPR. Yeah, this one. So here, this is the EPR. So this is my output file. Okay, this is my input file, this is output file. You just select it here, open here. So this is the structure what I got after optimization and frequency calculation. You just right click here and you just go to the summary. So it will give the all the data like what is the energy, all those things. Okay. So once it is done, now you need to create the input file for the EPRs. Till here, for EPR calculation, same thing. You need to do the your molecule, whatever the molecule you're taking, but keep in mind that your molecule should contain at least one unpaired electron. Okay, then only you can do that. Usually you can do it for free radicals or metal transition complexes. Then you go for the draw the structure, do the optimization, do the frequency calculation. So once it is done, so now you need to create the input file using this one. How to create the input file for EPR calculation? The same thing. You just select this one. Now you need to find out the coordinates. You can submit any kind of calculation. Just go to the here. Let me open this input file. Go to EPR here. Let me close this one. So these are my folder of this output file. So these are the file I have created for the This is the input file for the EPR calculation. This is the output file what I got. So let me open it. Open Notepad plus plus. See here. So this is what I'm doing here. So like this, you need to prepare your input file. So to save it your because you need to get the coordinates of your optimized structure. So this here these are the coordinates of optimized structure. To get that, let me minimize it. Uh, I'll just minimize this one also. So you just submit any kind of calculation. Just you need to coordinates, right? You just go to calculate, then go to Gaussian calculation setup. Now just type on the energy, then go to method. So like whatever the things you want to do, just let me. You are going with the DFT method. Ground state. You are going with the default spin. Let me consider, and you are going with yeah. This one is already because I did the optimization using the different basis set. Okay, you can because here like you can use various kind of basis sets or methods. And let me consider you are going with the here default spin with DNP. This sets you can go with the yeah. I will go with the same thing. Now let's consider you want to save this file. You just click on the preview. So here you will get the different coordinates because we are more interested about these coordinates. Okay. So we are more interested about these coordinates. Then you know how to save this, right? You just save this one and you can modify this file. Otherwise, just you copy these things. Whatever the things are there, you can copy and you can go to your notepad or notepad plus plus. Here, let me open it, and you can just place your coordinates here, and you can this one is the charge of your molecule and this one is the spin, and this is the here you need to provide name, and the same thing percentage chk is equal to name of your file chk. Here you can assign the memory like 6 milliwatt mw, not milliwatt it is uh, here you can 2 GB. Better you just go with the 2 GB. It will take less time. Processor you will go with the 4 depending on your system. And the thing you need to change compared to other input file, the thing you need to change is this one. So here you need to go with this method. You can use the basis set whatever you want. Either if you are going with 6311G, you give it this one. If you are going with 3211G, you can do with various types of this one. From here you need to take care of these things. You need to give these things. You need to write SCF is equal to tight, then space, property is equal to EPR. So this keyword will help us to calculate the EPR result. So electron paramagnetic resonance spectra, it will help us to calculate. Then pop is equal to minimal. So this is a keyword. Like this, you have to remember these things while calculating the EPR spectra. I will share if you want, I will share this input file. You can use it for your reference studies. Once it is done, you know how to submit the job, right? Once your input file is ready, and you already you know how you can submit the job by using the this Gaussian software. So already have submitted the job, done the job. Let me open the results. Here, this is my output file. Let me open it. EPR. Let me minimize it. EPR. Here, these are my output file. This is the output file. I will open through software only. Go to file, open EPR. This is output file. So this is what output file I got after this EPR calculations. Like we can right click, then go to the results here. Here you won't get any kind of extra properties here. Okay, you can go with the summary. It will show the same thing. So here you won't get anything by Gauss view. You can't analyze by software. It won't because it won't give the spectra. Okay, here by in Gaussian, it won't give the spectra. If you want to draw the spectra, EPR spectra, then you need to go some additional software you need to use like multifin. Using that one, you can just by giving some commands, you can create the your EPR spectra. But here you will get some of the values. Those values are very important. Let me open that. I will just open this input file. Once your job is done, you need to open the log file. This is the output file. You just open it in Notepad plus plus. So this is the output file. So by using this file, you can do the analysis. You just scroll down here. If you just come down, so this is a file. If you come down here, you'll get some data here. Yeah. So these are the some of the data. So these are the important points. So after calculating your EPR calculation, So you can calculate the what is the different isotopic fermi contact coupling values for your different ions, titanium ion, different fluoride ions. So these are the values. So in terms of megahertz. So by using these values, you can explain like how the exactly the electron density is distributing your molecule, how the spin transition is taking place. So whether it is how the interaction is going on, whether spin interaction is there or not, from where to where it is going on. Depending on this value, you can do that. But I'm not going to go more detail about these things. This one is one important thing. If you come down and you can some those who are interested here, you can go with these things also. Anisotropic spin dipole coupling constant value for each element. For each element, it will give the for each atom it will give the different like anisotropic spin dipole constant coupling value. These are the coupling constant value. By the, you can using these value, you can just go through some papers which are related to this EPR calculation. Then you will get to know that how exactly can you use these data. So like you can do that. But here by using Gauss-Pee, you can't generate the EPR spectra. So that is what I want to tell. So let me check what is remaining. So RY done, VCD done, ECD done, EPR done. Okay, we have done everything. This one. Okay. So UV visible spectra, emission. Yeah, we are left with these things, right? UV emission spectra and fluorescence spectra and photoelectron spectra. Okay. So here the even photoelectron spectra also. When you are performing the photoelectron spectra, just like how we did for the EPR spectra, that is the same thing. The only thing is for example, let's consider if you had the only changes is while preparing the input file name, you just change your name. For example, consider there is a molecule called A. For example, ethanol. For ethanol, you can calculate the photoelectron spectra, right? Now we are going to calculate the photoelectron spectra for electron. What you need to do, draw the structure of ethanol, then do the optimization, then do the frequency calculation. And directly you can't do the photoelectron spectra. If you want to calculate the photoelectron spectra, what you need to do? The same way, take the optimized coordinates of your ethanol, then you need to prepare the input file. So here, let me open this one. Uh, the same thing, the procedure is same. Yeah, this one. Let me open this input file in Notepad. Open with Notepad. Plus here. The same thing. The only thing you need to change is the this one. The property instead of EPR, you just need to put the electron. Okay, photoelectrons. Photo. You just keep it as a photoelectron. And here keyword you can use pop is equal to full. Also you can use, or you can use the pop is equal to minimum in case of while you are plotting while doing the photoelectronic studies. So I didn't did, but the same way that is photoelectron because using that Gaussian, you can't run this photoelectron spectra calculation directly. So first you need to create the input file. How to create? Before creating the input file, you need to draw the structure, do the optimization, do the frequency calculation, then take the coordinates of your optimized structure. You just click it here. Then you know how to prepare the input file name. Then depending, you can do it by using different basis set and functional method. And here the same thing, you just keep it here, and you just instead of property is equal to EPR, you just replace with the uh, this one photoelectron property, and keyword either you can go with the pop is equal to full, or you can go with the pop is equal to minimal. That is the same thing. And here also you won't get the any spectra in Gaussian. There also you need to open the log file and you need to do the analysis. But for those kind of like when you are focusing more on like electronic studies like UV or fluorescence or emission spectra or these photoelectron spectra, Schrodinger is the best one. Okay, so tomorrow I'm going to demonstrate you Schrodinger software. There I'm going to show you how we can perform these calculate these spectra. There you directly will get the spectra. These things that is very not like it is very easy compared to this Gaussian software. So tomorrow we are going to cover that. Then I will show you detail about how those photoelectron spectra, all those things. And similarly, when it comes to these fluorescence and emission also, here it's the same thing. I think you already know how to do this. The only thing is, I think you know right how to. Let me show it how to do the this energy calculation. So we did the energy calculation for ethanol, right? So how we did? First we draw the structure of ethanol. Then we performed the geometry optimization of ethanol. Then we took the geometry optimized structure. Then we performed the energy calculation, right? You need to open the log file of your optimization result. then we'll go for the calculation button. You just go for calculate and then go for the Gaussian calculation setup. So connection right is equal to geometry. Let me open it. Let me close it and I will open it from the beginning. Now let's consider you are interested to calculate fluorescence spectra for some emission spectra for your compound. So before that, let me talk about for 1 minute what exactly the difference between the fluorescence spectra and emission spectra. So usually what happens in fluorescence spectra, so fluorescence means it is like specifically refers to the light emitted by the substance when it is exacted by the some specific wavelength of light, right? So it involves the absorption of photons by molecule followed by the emission of photon as the molecule and return to their lower energy state. First we will absorb some energy, then they will go to the higher energy state. From there they will release some amount of energy in the form of photons. Then they will come back to the lower energy state. That is one kind of electronic transition, right? But when we talk about the emission spectra, it does not include only one kind of transition. So it includes it is like mixture of light emitted by like it in a substance. It includes the like along with the fluorescence, it includes the various types of like fluorescence, phosphorescence, chemiluminescence. Okay, even you can consider the thermal emission. So when you talk about the emission spectra, so we are going to talk about all kind of emission. Either it may be fluorescence, or it may be phosphorescence, or it may be chemiluminescence, or it may be thermal emission. But when you are talking about particularly that emission spectra, sorry, fluorescence spectra, that is exactly what happens. It will absorb some amount of energy from the and it will go back to the excited state. Then it will release some energy. Then it will come back to lower energy state. That is the particular the fluorescence spectra, right? So usually when you perform this emission spectra, we'll do these studies at the triplet state. For fluorescence spectra, will do at the singlet state only. The only difference is the same thing. Whatever the process you have followed for UV calculation, the same thing you need to follow the for fluorescence and emission spectra calculation. But keep in mind, your Gaussian software won't give the your fluorescence spectra and emission spectra. It will give only your UV spectra and E-series spectra. But it will generate the log file. From that log file, you can calculate the lambda max value or E max value. Based on that, you can by using some origin software, all those things, you can plot the your fluorescence spectrum depending on your lambda max, how much you're getting, E max, how much getting. You need to take the difference between all those things, absorption and emission. Then you can plot the those fluorescence spectra and emission spectra using origin software. Now let me show what is the difference here. Uh, let consider you just open your whatever. Let me show here. Let consider this is a structure of methane, right? Let consider it is optimized structure. Now you are going to calculate the energy calculation. Means you need to calculate the this one fluorescence spectra and emission spectra for this compound. Then go to calculate. Let first I will let me explain like how to calculate the fluorescence spectra. Go to the calculation setup here. You just choose the energy to calculate these things. What fluorescence and emission spectra, you need to do the energy. Then go to method here because these are the similar type of calculation. Then that's why I'm not submitting the calculation again and again. I'm just showing the method like how you can do that. And let here you can choose that whatever the method you want. If you want ground state, and you can go with the yeah. So sorry, this one thing is whenever you will do the energy calculation, you need to choose the time dependent SCF. Then you can go with the method like DFT method, I can artifact method. It is up to you what kind of study you want. Go with the default spin B3L by P, this one, and then let me go with some higher basis set. Let me, everything is same, okay? The only thing we need to change is, let me P here. The charge now is 0 and it is a singlet state. Now the number states here. So if you give it the default, it will go for the your DFT calculation. And okay, if you keep it as a default, it will do the DFT calculation. If you keep it as a singlet and you just click on this solve more state and you can give it for like another 5 to 10. It is up to you how many state you want. Okay. And you can give the state of interest. You just select it. You can keep it 1 or 2 or 3. Just keep it like 3. It is up to you how many you want it like this. So during UV calculation, we'll just go for the default, right? We can go for the default, and then we won't activate. If then also you can activate it. Okay. So when you UV also will activate. You can do the UV calculation by using singlet option. You can calculate this as thing. Then if you give 10, then it will show 10 possible transitions. Okay. So like that, the same thing, you just submit the job, and along with your UV calculation, it will do the fluorescence calculation also, but it won't show in your here, Gaussian, just by reading your output file, log file, you get to know. But better than that, you just go with the squad engineer. I will explain you how they will directly will get the fluorescence spectra. That is the method, only method you need to follow for the fluorescence spectra. Let's consider now you are interested to, now you are planning to draw, find out, calculate the emission spectra. So if you want to calculate the emission spectra, same thing. The only thing you need to change is instead of taking a singlet only, you just go for the triplet only. So when you click on the triplet only, it will calculate the different types of emissions which are taking place. But then after you need to do the analysis of your log file. From that log file, you will find like various values like your this one. It will give the different excitation energy, whether it is singlet type. If you give the singlet, then it will show only singlet type of transition. If you do the triplet along with the singlet triplet, you will only triplet will give. At the same time, you can go for both fluorescence and emission. In that case, you need to choose the singlet and triplet. So this option you need to choose. Okay. Usually for this UV and fluorescence, for emission, you can go with the triplet only. Then, for example, if you want both, you can go with the singlets and triplet. At the same time, you have to keep in mind that it will take more time. And here, like a number of states, you can increase. You can. It is up to you. Like, but as the number of NU increases, the time required to perform the calculation also increases. Okay, so like that you can do the calculation. I think, let me, I don't know whether I did it or not. So let me check it. Like, I think during my last workshop, I think I did it. Mm, I don't know whether it is in Drive or not. Let me close this. I think somewhere, like, let me download. Yeah, one thing is, yeah, there is on fluorescence folder is there here. So let me open this Gaussian input file, output file, these things. Yeah, I think this output file, let me open it. So I did one for like open with, otherwise edit with notepad plus plus. So once you open your like output file after the job, if you come down somewhere, you will get some excitation energy values. Yeah, here, see here. So by going through this log file, okay, output file, you need to find out that what is the lambda max value, what is the Emax value. So here it will show what kind of it like singlet. These are like singlet transition. These for fluorescence calculation. I don't know if you want to do this fluorescence spectra. Uh, you need to take select as a singlet. In the same way, for emission spectra, you need to choose the triplet state, and you can, it will show like from where to where transition is going on. So from molecular orbital 116 to 118, it is going on singlet type of transition. So here it will show this is the like lambda max value 640.99 nanometer is the lambda max value, and it is like your strength of your oscillation. So how efficiency, how much, what is the strength of your oscillation? It is showing here. Uh, then like here, then your, this is the next excitation state. So by using these values, then you can plot the, this is the total energy of your system. By using these values, different values, you can plot the your fluorescence spectra by using, either you can use draw it by using origin, or you can go with the multi-fin, or you can draw this spectra with the Excel also. You can use your MX Excel also, you can draw it, but the origin is the best one. You can create some very good spectras by using the origin software. So if you know how to do that, you can just go this take value. And the similar way, if you do the emission spectra also, you will get the same kind of output file. So by using this output file, you can do the you can draw the your emission spectra of your molecule. So, but for those fluorescence emission, you need to use some external spectra, because like how you're getting ready-made spectra like IR, Raman, ECD, VCD, these NMR, in all the cases, you are getting the ready-made spectra in there, Gaussian software itself. But when it comes to the EPR spectra, or some photoelectron spectra, or fluorescence spectra, emission spectra, You can calculate by creating the output file, by creating the input file and you're submitting the job in Gaussian software. But at the same time, it will give the log file. It won't give the spectra directly. By using those analyzing log file, you can create the spectra. I think we have, now we have covered everything what I have mentioned in the brochure. We are left only with the adsorption studies and catalysis studies. And that one, I won't go with the Gaussian. Either I will explain that thing with the, either with the Schrodinger or with the quantum espresso. From today onwards, I did finish the your Gaussian software. So tomorrow, in one day, I'm going to explain, demonstrate you how to uh, perform the DFT calculation using the Schrodinger. After that, already have mentioned in the group, I'm going to take 2 more days till like July 11th and 12th. In the 2 days, I will try to explain that the quantum espresso. I will don't go deeper into that software. Just I will show you like how to install that software. Then how I will explain like what are the different menus which are there, how to use that one, then how you can set up the different parameters to calculate. Then I will show you how to calculate band structure, how you can calculate the density of state. All those things I'm going to cover there. Okay. So if you have any questions, please write in the chat box. So that is today what we have planned. So if you have any questions, please write in the chat box. So if you don't have any questions, I will just close the meeting. Thank you one and all for your time and patience. See you in the next class. Good night.